Welcome to Lecture 16b. We will discuss subspaces of a vector space. Last time, we talked about how most concepts in this class can be described in terms of addition and scalar multiplication. That is, if we know how to add two things and how to multiply by a number, then we can define almost everything we have defined in this class in terms of that. The big idea is that there are other things that we can add and multiply by a number besides vectors. We can add and scalar multiply polynomials, functions, sequences, matrices, etc. This led us to generalize the notion of a set of vectors to a vector space. A vector space is a set of mathematical objects where you know how to add them, you know how to multiply by a number such that 8 axioms hold. These 8 axioms are just a list of properties that tells us that addition and scalar multiplication must behave in a nice and familiar way, like vector addition and scalar multiplication for vectors. We had a warning that a vector space is a set of objects that behave like vectors. They're not necessarily vectors, even though our textbook uses the word vectors to describe elements of a vector space. Last time, we saw many examples of vector spaces. The first is the motivating example, Rn, the one we studied all semester. The set of polynomials in X is also a vector space. Addition and scalar multiplication are defined in a familiar way for polynomials. We can also restrict ourselves to polynomials of degree at most n. So for example, here P2 denotes the set of polynomials of degree at most 2. This allows us to work with a smaller set of polynomials. Addition and scalar multiplication are defined the same way as in the bigger set P, the set of all polynomials in X. The set of sequences is also a vector space. You can add two sequences term-wise, and you can multiply a sequence by a number, also term-wise. The set of matrices of a fixed size is also a vector space. For example, the set of matrices of size 4 by 5 is a vector space. A smooth function is a function where all its higher derivatives exist, first derivatives, second derivatives, third derivatives, etc. The set of all smooth functions, denoted by C infinity, is a vector space. You can add two smooth functions together and get another smooth function. You can multiply a smooth function by a number and again get a smooth function. The reason we include this last example is because if we want to apply linear algebra to differential equations, we must work with the vector space of all smooth functions. A direct proof that a set is a vector space requires checking 8 axioms, which is a lot. So we are not going to check all 8 axioms in this class, but there is a situation in which we don't have to check the axioms. Let's say we already know that V is a vector space. So V could be one of the examples in the previous slide. Given a subset W of the vector space V, we can define addition and scalar multiplication in the smaller subset by just using the same definitions as in the bigger set, which is a vector space. This trick only works if the sum of two elements in W is still in W and the scalar multiple of every element in W stays in W. If this works though, all 8 axioms would happen for free because we know that all 8 axioms are satisfied in V, and we know that V is a vector space. So we can inherit all 8 properties from the bigger set V without needing to check each of the 8 properties. Here's an example. We already know that P, the set of our polynomials, is a vector space. But let's say we don't already know that P sub 3, the set of polynomials with degree at most 3, is a vector space yet. But the point is that in P3, we don't need to define new rules for addition and scalar multiplication. We can use the same rules as in P. So to add two polynomials in P3, the smaller set, just add the two polynomials as in the bigger set P, and just check that the result is still in P3. Scalar multiplication is defined the same way, and also just check that if you do a scalar multiplication on a polynomial in P3, then that scalar multiple stays in P3. Since the axioms for addition and scalar multiplication hold in the bigger set, they automatically hold in the smaller set. So P3 is a vector space. The reason we can conclude this is because of these two properties. The fact that adding two polynomials in P3 stays in P3, and a scalar multiple of a polynomial in P3 is also in P3. If we take a different subset where one of these does not hold, then we won't be able to have this conclusion. Let's consider the set S of polynomials of degree exactly 3. Then x cubed plus x and negative x cubed are both polynomials in S, but their sum x is not, because the degree of x is 1 and not 3. So S is not closed under addition. Because of that, we would not be able to use the same argument as we did with P3 to say that S is a vector space. We already have a name for this phenomenon for something that is close under addition and scalar multiplication. Let's reuse that name. If V is a vector space, a subspace of V is a non-empty subset W of the vector space V, which is close under addition and close under scalar multiplication. This is one of the many times that we will take a definition we already know, we cross off Rn and write vector space instead. Since the original definitions for addition and scalar multiplication in the original vector space work for the subspace inherits the nice properties of the original vector space. So the subspace of a vector space is again a vector space. So many of the concepts we have been working with recently, subspaces, bases, and dimensions, are concepts we are doing for vector spaces. Many of those ideas will generalize to other vector spaces. We will now do these two exercises. For both of them, the idea is to use definition 4 to either show that a non-empty subset is a subspace by checking properties 1 and 2, or show that it is not a subspace by coming up with a counter example. In this first exercise, let V be the set of polynomials with a factor of x plus 1. And we want to show that V is a subspace of P, the vector space of all polynomials in X. Not every polynomial has a factor of x plus 1, so the set V is smaller than the entire vector space P. To show that V is a subspace, we need to show these three conditions. The first thing we want to show is that V is non-empty, which means we need to find at least one polynomial with a factor of x plus 1. But x plus 1 is a polynomial with a factor of x plus 1. You can think of it as x plus 1 times 1. So x plus 1 is in our set V, so V is non-empty. An alternative way to show that V is non-empty is I could have checked that the zero element of P is in V. The zero element of P is just the zero polynomial, 0. 0 is equal to x plus 1 times 0, so the zero polynomial is in V. Next, we want to show that V is close under addition. Just like in the case for Rn, we want to start with saying let some letter and some other letter be in the subset in question. So I say let P and Q be in our set V. And then I want to write down what it means for P and Q to be in V. So we have to look back at the rule for being in V. Being in V means that P is equal to x plus 1 times some polynomial f. And for Q to be in V means that Q is equal to x plus 1 times some polynomial. Here I have to choose different letters because P and Q might be different elements. Let me now erase these comments to make room for me to finish showing property 1 and property 2. After writing down what it means for P and Q to be in V, I need to do some computation to show that P plus Q is also in V. So I need to show that P plus Q is also a polynomial with a factor of x plus 1. So P plus Q is equal to where I can replace P with x plus 1 times f, and I replace Q with x plus 1 times G. I have a common factor of x plus 1. This shows that P plus Q is equal to x plus 1 times f plus G, but f plus G is a polynomial. So P plus Q is in our set V. So V is closed under addition. To finish answering this question, I just need to show that V is closed under scalar multiplication. The format is going to be the same as when we were working with Rn, the vector space of factors. To show that a subset is closed under scalar multiplication, always start with saying let a letter be a number and let another letter be in the subset in question. So I write down let C be a number and let P be in our subset V. And then we want to write down what it means for P to be in V by checking the rule for V. Being in V means that P is equal to x plus 1 times f for some polynomial f. Our goal is to show that C times P stays in the subset V. So now we will do some computation to check that. I will substitute P with x plus 1 times f. I can move x plus 1 to the front, and I have that CP is equal to x plus 1 times CF, but CF is a number times a polynomial, and so CF is still a polynomial. And so CP satisfies the rule of being in the subset V, so CP is in V. So our subset V is closed under scalar multiplication. We have checked all of these properties. So our subset V is a subspace of P. This is the end of the answer for exercise 2. In the next slide, I will show you a sample student answer, which you can use as a template for your homework. So whenever you're trying to show that a subset is a subspace of a known vector space, you would follow this very same format. You show that the set is non-empty by just making sure there's one element satisfying the rule of the subset, and often you can just use the 0 element. And then you also want to show that the set is closed under addition, and you start the same way by saying let 2 elements be in your subset, and then you write down what it means to be in your subset, and you show that P plus Q, the 2 elements, stays in the subset. To show that the set is closed under scalar multiplication, you always start the same way. Let C be a number and let some letter be in your subset, and then you do that number times your element, and you check that this new element stays in your subset. And you do have to check the rule of the subset. Once you do that, you show that this subset is a subspace of your bigger set. Now let's look at exercise 3. Here we consider S the vector space of all sequences. Let W be the set of sequences beginning with 1. So I have a list of numbers where the first entry of that list should be 1, and then the other entries can be anything. We want to show that W is not a subspace of S. We need to show that one of these three properties fails by giving one concrete counterexample. You should be as specific as possible in your counterexample. Let's look at this first property. But I see that W is non-empty because, for example, the sequence of all ones is in W. So I wouldn't be able to have a counterexample here. So what I should do is find a counterexample for either 1 or 2. I should find either 2 sequences in W so that their sum is not in W, and that will be a counterexample for property 1. Or I should find one number C and one sequence in W so that the number times the sequence is not in W. And that would show that the second property fails. It turns out that in this case, it is very easy to find a counterexample. Let A be the sequence where all entries are 1. This set is in W because the first entry is 1. I can take the sum of A and A. Remember that the rule is to do term-wise addition. So I just do 1 plus 1, 1 plus 1, 1 plus 1, and so on. This gives me a sequence where all entries are 2. Since the first term of the sequence A plus A is 2, which is not equal to 1, the sequence A plus A is not in W, so W is not closed under addition. Therefore, W is not a subspace. Let me give you an alternative answer where instead of showing that W is not closed under addition, I will show that W is not closed under scalar multiplication. We only need to do one of these because if one of these fails, then the subset is not a subspace. Here, I will let A be the same sequence as before, the sequence where all entries are 1. Then A is in W. Now I will pick any number that is not 1, and that will turn the first entry to be a number that is not 1. Let me use 5 for my number. Scalar multiplication for sequences is defined term-wise, so I just do 1 times 5, 1 times 5. So I get a sequence where all entries are 5. I see that the first term of 5 times A is 5, which is not equal to 1. So the sequence 5A is not in our subset W. Therefore, W is not closed under scalar multiplication. So our set W is not a subspace of S. There are many examples of subspaces of vector spaces. Our favorite vector space, Rn, are themselves subspaces. All of these are subspaces of vector spaces. Many of the vector spaces we have talked about are subspaces of other examples. For example, each of the P sub n is a subspace of P, the vector space of all polynomials. We talk about how the set of all matrices of a fixed size is a vector space. If we consider the set of all matrices of size 3 by 3, this is a vector space. And it turns out that if we take the subset of symmetric 3 by 3 matrices, this actually forms a subspace of the vector space of all matrices of size 3 by 3. This big set of all polynomials turns out to be a subspace of this bigger set C infinity, the space of all smooth functions. So here we have a chain of containment of subspaces. P sub n is a subspace of P, and P is a subspace of the bigger set C infinity. Let us now do an exercise involving C infinity, the vector space of all smooth functions in X. Here, S is the set of smooth functions so that the second derivative of f is equal to the negative of f. And we want to show that S is a subspace of C infinity. So we need to first show that S is not empty, meaning we need to find a smooth function where the second derivative is equal to the negative of that function. We also need to show that S is closed under addition and under scalar multiplication. This should be very similar to all of the other times when we show that a subset is a subspace. Note that the definition of S is saying that S is just the set of solutions to the differential equation second derivative of f is equal to the negative of f. So to show that f is non-empty, we just need to come up with one solution to this differential equation. Recall that the function sine of x is smooth. All higher derivatives of sine of x exist. The first derivative of sine of x is cosine of x, and the first derivative of cosine of x is negative sine of x. So the second derivative of sine of x is the first derivative of cosine of x, which is equal to negative sine of x. So sine of x is a solution to this differential equation. So sine of x is in our subset S. The zero function also works because the second derivative is just 0, which is equal to negative 0. So this was my scratch work. My actual answer is written here. I can just say that the function sine of x is smooth. All derivatives of sine of x exist, and the second derivative of sine of x is equal to negative sine of x. So S is non-empty. Next, I need to show that my subset is closed under addition. To show that S is closed under addition, I write let two elements be arbitrary elements in the subset, and I write down what it means for these two elements to be in the subset. And then I have to do computation to show that the sum of the two elements is also in the subset. Let F and G be in S. This means F and G are smooth, and F double prime equals negative F, and G double prime equals negative G. Then we need to show that the sum of F and G stays in S. F plus G is also smooth. This is because C infinity is a vector space, so C infinity is closed under addition. Next, I need to do computation to show that the second derivative of the sum of f and g is equal to the negative of the sum f and g. One of the properties of derivatives is that the derivative of a sum is the same as the sum of the derivatives. So these two expressions are equal, but f double prime is the same as negative f, and g double prime is the same as negative g. So the second derivative of f plus g is the negative of f plus g. Therefore, f plus g is in S. So our subset S is closed under addition. Finally, we need to show that S is also closed under scalar multiplication. We follow the same format. We say let some letter C be a number, and then let another letter denote an element in our subset S. And then we have to write down what it means for F to be in S. And then we have to show that the number C times F is in our subset, and we might need to do some computation to show that. Let C be in R and let F be in S. And then I need to write down what it means for F to be in S. The rule for this particular subset is that F has to be a smooth function and F double prime equals negative F. I need to show that C times F is in S. To do that, I need to explain that C times F is smooth and C times F double prime is equal to the negative of C times F. C times F is smooth because C infinity is a vector space, so C infinity is closed under scalar multiplication. Let me write down CF double prime. Here it says that F double prime is equal to negative F, so this is equal to the negative of C times F. So C times F is in our subset S. Therefore, S is closed under scalar multiplication. Hence, S is a subset of C infinity. I will now erase my comments and put all answers into one page. When you do a homework for showing that a subset is a subspace, you can use this answer as a template. The previous exercise is an example of a more general phenomenon. If I have a differential equation, it is not always true that this set of solutions forms a subspace, but if the differential equation is a linear differential equation, then its set of solutions forms a subspace of C infinity. So it follows that the solutions to a linear differential equation form a vector space. I'm not going to give you the definition of a linear differential equation. I only wanted to tell you about an application of vector space theory to differential equations. This theorem allows us to use the techniques of linear algebra to study the vector space of solutions to a given linear differential equation. For example, here is a big theorem in differential equations. If I know a bunch of solutions to a linear differential equation, then any linear combination of those functions is also a solution. A big part of differential equations is finding a few solutions and knowing that you can get all the solutions as linear combinations. I will end the lecture with two examples of sets whose elements are quite different from vectors. Recall that P sub 2 denotes the set of polynomials of degree at most 2, and this set is a vector space. In this first example, let S denote the set of polynomials in P2, where if you plug in 5 into the function, you get 0. And we will determine whether S is a subspace of P2 or not. First, I will try to show that S is a subspace by showing all these three properties. If one of them doesn't seem to work, then maybe S is not a subspace, and I will try to find a counterexample. To show that S is not empty, we just need to come up with one polynomial where if you plug in the number 5 into the polynomial, you get 0. The polynomial x minus 5 is in P2. The degree is 1, which is less than 2. And plugging in 5 into the polynomial gives us 0. So x minus 5 is in S. This shows that S is non-empty. Let me now try to show that S is also closed under addition. Let f and g be two elements in S. I need to write down what it means for f and g to be in S. F and g should be polynomials in P2, so the degree should be 2 or smaller. And also, if I plug in 5 into f or g, I should get 0. I then need to consider f plus g. I need to show that f plus g is a polynomial also in P2, and that if I plug in 5 into f plus g, I get 0. If I add two polynomials, and each of them has degree 2 or smaller, then the sum also has degree 2 or smaller. If I plug in 5 into f plus g, this is the same as f of 5 plus g of 5. F of 5 is 0 and g of 5 is 0, so I get 0. Therefore, f plus g is in our subset S. So S is closed under addition. This is hopeful. If we can show the last thing, then we can show that S is a subspace of P2. To show that S is closed under scalar multiplication, we start the same way as usual. We say let C be a number and let F be in our subset S. We then write down what it means for F to be in S. It means that F is a polynomial in P2, and if I plug in 5 into F, I get 0. And then I need to show that C times F is also in S. To do that, I need to say that C times F is also in P2, and if I plug in 5 into C times F, I get 0. But C times F stays in P2 because the degree is not going to increase by multiplying by a number. When I plug in 5 into C times 5, I can move C out, and we know that f of 5 is 0, so this becomes 0. So C times F is in our subset S. Therefore, S is closed under scalar multiplication because we have shown all these three. We can conclude that S is a subspace of P2. I have erased my comments and put the entire answer in one page. Please use this as a template. Now let's look at this next exercise. I am working with the same bigger vector space, which is P2, but I define my set T to be the set of polynomials in P2 so that if you plug in 5 into the polynomial, you get the number 1 instead of 0. And again, we want to show whether this subset is a subspace or not. Before I show you my answer, let me explain my thought process. I'm not sure yet whether T is a subspace of P2. So first I will try to show that T is a subspace. So I would have to check all three conditions. It's pretty easy to come up with a polynomial of degree 2 or smaller so that plugging in 5 into that polynomial gives me 1, x minus 4 as an example. So T is non-empty. So let me next try to show that T is closed under addition. But if I have two polynomials, let's say f and g in T, then if I plug in 5 into f plus g, I would get f of 5 plus g of 5. So I would get 1 plus 1 equals 2. So I don't think that T is closed under addition. So what I have done here is not giving a specific counterexample. I need to come up with two actual polynomials in T, where if I add up the two polynomials, I get something that is no longer in T. Let me come up with a counterexample. I will try to use the same polynomial, x minus 4. So I write down let f be the polynomial x minus 4. I have explained before that x minus 4 is in T. I can choose a different polynomial, but let me just choose the same one. F plus f gives me x minus 4 plus x minus 4, which is 2x minus 8. I plug in 5 into f plus f. This gives me 2. Since f plus f of 5 is not equal to 1, f plus f is not in T, so T is not closed under addition. Therefore, T is not a subspace of P2. I have erased my scratch work and put the same answer on the next slide. Please use this as a template for your homework answer. I could have chosen to answer this differently. I could also find a counterexample to show that T is not closed under scalar multiplication. Here I'm using the same polynomial, x minus 4. We know this is in T, and I can choose, for example, the number 4 to multiply f by. So I take 4 times f. This gives me 4x minus 16. I can then plug in 5 into 4 times f. This gives me 20 minus 16, which is equal to 4. And 4 is not equal to 1. So 4 times f is not in T. And so T is not closed under scalar multiplication. Therefore, T is not a subspace of P2. This is the end of lecture 16b. Next time, we will continue talking about vector spaces, but in the context of bases and dimensions. Thank you for listening.